Welcome back. So the next thing I want to talk about with using these matrices is something that people will find quite confusing, but hopefully we'll introduce it and we'll keep coming back to it, and you can get it throughout this term. Um, I want to be thinking about transformations as bases. Transformations as change of basis. It might be worth your while if you haven't done linear algebra in a long time, or you forget what a basis is. It might be worth your while to pause the video and Google what's a basis in linear algebra and read some quick, just to get yourself back into the mind space. So I'm going to explain it briefly, but this is no replacement for your linear algebra textbook, okay? So if we transform geometry, transforming we can think about it in many cases as just changing the basis or the coordinate system. This is something I've said before, and it felt kind of random at that time, but now with bases we can think about them as actually as coordinate systems. So this is a key point. When we do transformations, we are actually presenting the same data. Okay? It's the same data. It's the same points. They're just transformed. We can go back, right? So if we think of it that way, then it helps us visualize the coordinate systems and how they work. So let's talk about the standard basis. And hopefully this will help you understand what the heck I'm talking about. So I'm going to draw this coordinate system like that. Okay, this is our standard coordinate system. This is my x, this is my y, okay? Now I'm going to draw a point in there called P. We know what this means. We know it's a coordinate. We're not surprised by that. But using the basis definition, I'm going to say, well, actually x has the following vector as the basis. X of 1, y of 0. Right there. That's the vector that defines the x. And then y will also have a vector that defines the y-axis. Okay? And that's going to just be x of 0, y of 1. So these are my two basis vectors. These two vectors define the coordinate system. Any point in my coordinate system I can define in terms of combinations of these two vectors. And that sounds kind of crazy if you haven't thought about it in a while, but that's exactly what we do every single time we give a point. Oh, this point is at 2.5, 2.5 comma 2, right? If we did that, what we're actually saying is we're 2.5 times along x and 2 times along y. That's all that we're saying. But it's longhand, so we don't often say it. Now I can write this out in a more standard linear algebra form. So we can say that a point in space is some origin plus a basis times the point in that local coordinate system. Okay? So in this case, our origin here is 0, 0. So let's write that out. 0, 0, that's good. Plus our basis. Now, you probably don't remember this, but you can construct your basis by just putting the vectors in columns. So I'm going to put the x first. The x, I'm going to get this wrong. I got it good. This is my x, and then I'll get the y, which is 0, 1. So this is my y. I got to turn that off. This is my y, and this is my x. And then I multiply that by px and py in the local coordinate system within my basis. Now, this is like, you might be looking at this going, this is kind of crazy, Jim, because first of all, adding 0 does nothing. Great, it's a standard coordinate system. The origin at 0, 0, nothing changes. And then, hey, Jim, that's the identity matrix. If I multiply that by my point, I just get nothing, right? Which is exactly what we want in our standard basis. Nothing. This is exactly, it's circular logic because it's the whole definition of this basis. So we can define this p in terms of those basic vectors. This seemed like a waste of time, but we might want to, we can now start thinking about our other transformations or our other displays in the same kind of way. So I'm going to write this out. Where am I? So we can specify any point in an n-dimensional coordinate system. This is important because it's not just 2D, it's 3D and whatever you want as well. As a linear combination of n, that should be an f, linearly independent vectors. Another way to say linearly independent is orthogonal. Okay. So we can specify any point as a linear combination of orthogonal vectors. Well, this is good because these are I have a two-dimensional space, I have two orthogonal vectors, I can specify any point in a combination of x and a combination of y. But it goes beyond that. It goes to, we can have any coordinate system. So here's my standard coordinate system, and I'm going to draw a new one within here. I'm like, okay, this is my new x. I'm going to call this my x as my basis, and I'm going to draw y. And these are orthogonal, okay? And then now my point P up here, I can express this in terms of the standard coordinates, how much of this x and how much of this y, or I can project that on my basis, and I can say, hey, look, if I have this much of this vector and this much of that vector, I'll come back to my point. So P, how should I write this? I did it over here. So P is going to be the origin, which is this point there. I should write that in, hey? It's going to be the origin plus, where's the, that's not like a plus, where am I? There it is. Plus the x coordinate, how many along there? So the x basis times the x coordinate, and then the y, this is a vector, there we go, y basis times the y coordinate. So what this means is I take the origin here, I add in, okay, this many times that vector, and this many times that vector. If these are standardized to length 1 here, for example, it's 1, 2, 3 times that vector, plus 1, 2 times that vector, whatever. But in this case, the vectors go really long, so it's like 0.8 times that vector. It doesn't really matter. You can standardize them to be the same scale, but it's some of that vector plus some of that vector will get you to that point offset by the origin. So we can do this with any transformation. We can think of any point as being defined by that coordinate system. Now, I found this concept very helpful in a few places in my professional work. So this concept helps whenever you need to go between coordinate systems, basically. When you need to go back and forth between different coordinate systems. Now, I'm going to come back to basis later in the unit, but you'll see what's really cool about this is the math turns out to be really, really simple. It looks complicated. It is complicated inside your head, but the math is really, really simple and really fast. So I've used this in robotics. I've used this in motion capture. I've used it in motion planning. I've used it in animation. It's used in deep learning now. This idea of using a basis to switch coordinate systems comes up everywhere. So, you know, this is something that's good for you to get review on. Now, I'm going to go back to this demo that I ran earlier. I'm going to put that in my notes. Sketch 1. We can talk about this a little differently now. I have this hourglass which I've defined in the standard coordinate basis at 0, 0, say here. Right? I'm at 0, 0. I go, one vector out, I'm here, one vector up, I'm there. It's a coordinate system. When I redraw it, look, it's the same thing just in a new basis. Okay? I have a new vector here. I go along 1, I'm at this point. I go up 1, I'm at this point. Because the basis is rotated, the whole object is rotated. This is a nonlinear, a non-orthogonal basis. We can do that too. We can skew things. It doesn't matter. We can skew them. Although technically a basis you want to be orthogonal and to make sure you can cover all the points. But that's it. So this is an example of things when you do the transformations. You're just drawing them in new coordinate systems. Okay. Where am I? Yeah. So constructing a basis matrix for known vectors is trivial. Right? I put the x there, I put the y there. If I knew, I could write. I'll write it out. It wasn't in my notes, but I could write the basis for this one as x. But this is my x coordinate. That's in small x and y, and then my y x, my y y. So if I have those two vectors, I make a matrix out of it. Now I can multiply this by any point. If I multiply it, it'll bring me out to world. I shouldn't say world coordinates yet. We'll come back to that. I'm going to say to the standard coordinate system. So if I know those two vectors, I can use it to build the basis. Nothing. I'm done. I just put them right in there, and I'm done. And I can use that basis to multiply any point in that local system to bring it back to the standard. But what if I want to go the other direction? What if I want to go in the other direction? If I have a point, px, py in standard system, in the standard coordinate system, how do I bring it into my local? How do I find out where it is in that local space? Well, if I have the matrix to bring me from that coordinate space to the world space, I can just invert it. Right? So I could go basis invert times that. It'll go in the opposite direction. So it's really, really nice. I just invert that matrix, and now I have a matrix that brings me to the local coordinate system. It gets better. And I probably should want to switch away from green. It gets better. Well, what if our vectors are unit vectors, are length 1, and we know that they're orthogonal, then we have an orthonormal matrix. Does anybody remember what the inverse of an orthonormal matrix is? It's just a transpose. So I can lay them out this way and I go one direction. I lay them out this way, I go another direction. It's just so easy. Getting your head around how it works might not be so easy, but doing it and using it, there's nothing to it but a few multiplications. So this is, my notes won't work again. All I'm really going to say about basis vectors, and you can look those up on your own. I'm not sure yet exactly how much this specifically will come up in your assignments, but it's really useful to know and a really useful lens that you can use to look at all the transformations that we're going to be doing. Okay, so let's come back and learn some more about coordinate systems.